Okay. So we're recording now. If you're not okay with recording, it will certainly be not available publicly, but if you're still not okay with it, please tell me. No, but I guess since the lecture is recorded, it should be good. Okay, good. Then let's continue with part C. Yeah, some are still optimizing our function, but let's continue. But thanks for that. Update the eval function so that it supports a new var constructor and use it to get a numeric value of the expression C1. Okay, that's maybe let's just copy the function down here and call it C and give it a new name like eval prime. So for now, everything is okay. And now we add a case for variables. We have a variable with some name. What should we do? Please let me know if I'm decreasing the font too much. Yes, thanks for the answer. We should use our new function and look up what value this variable should have. And now we can evaluate our expression C1, hopefully. No. I used the wrong function. No, I didn't. I have a non-exhaustive pattern. Yes, you're right. That's the point. I did a stupid copy-paste error. What happened is I called the old function up there. So I really could have introduced a nasty bug here, but we found it luckily by our exception. Okay. Minus 2,600. Yeah, well, let's look if that should be the right result. We have this one is 13. Here we should get 20, 8 plus 12. So 20 times 13 is 260. So this already looks good. And here we get minus 10. So works correct on one example. That's certainly not trivial. Okay, now the question is how we should continue. That was exercise 1.1. There's also an exercise 1.2, which is slightly different, a bit more complicated. The expression type is a bit more general. I highly recommend that you do that for yourself at some point to recap what we did here and do it a bit more general, practice a bit. I guess that's good. Now, this is one of the bonus exercises you can hand in, this one as well. And what I want to talk about is this one. So exercise 1.5 says, it's a more theoretical one, which I'm not sure I would solve in Haskell. I would use Haskell, but I still might write it down on paper if I had to give in some hand in. Functions as tuples. So for any type T, well, it's a bit abstract, the type functions from bool to T is basically the same as the type TT. So let me explain all the ingredients here. Bool is a data type with two values called true and false. So that's what you would expect, I guess. And this type here is what you would call in math a Cartesian product. So you have the type of pairs where both the first and the second component are of type T. Okay, and now the exercise says two types are basically the same, whatever that means. So we have a type of functions and a type of pairs. I'm always marking the wrong thing here somehow, but anyway. Okay, so now it says implement two functions which go both directions from this function type to this pair type and the other way from the pair type to the function type. And they are called ISO-R and ISO-L. Okay. Do you want to break? I'm not used to this, sorry. How long is a break usually? Ten to 15 minutes. Well, okay, good. Let's have a break then. That's good. Yeah. Then we will continue in 13 minutes, I would say. Okay. Good. Thanks so far, everyone, for participating. Okay, welcome back, everyone. We continue the demo session. A question. How does the bonus pointing system work? So there should be an announcement soon about that. You can hand in one of the bonus exercises. So I don't know if it was announced in the lecture, but let me look it up. This week, you should hand in 2 of 1, 3, 1, 4, 1, 8, and 1, 12. So yes, 2 of this set. And yeah, that sounds about right. And okay, someone posted a link. Many thanks. Yeah, but let me finish the explanation. If you you can get 1 point, which will count in the exam in the end. So I think there are 100 points, and so you can get a small bonus, and well, it's supposed to be a motivation. So it's supposed to work like this. You write, you hand something in, so you can submit it to Canvas in some way. You will be informed about, and then, oh, that might be the wrong link about assignments. So assignment is something different. So oh, no, okay, it's the right one, sorry. So yeah, that's the right text. Yeah. And so you hand something in via Canvas, and then 10 students that handed something in get randomly selected, and we ask those 10 about their solution. And well, it has to be correct to work. It doesn't have to be very good or something like this. It has to be a solution, and we have to be able to believe you that you did it yourself. Okay, but there will be an announcement about that. Okay, and there are also group assignments, but that will come later. Okay, very good. So let's start a new file, call it x115. No group assignment this week. Yes, that's correct. So the group assignments, there will only be 2 in the whole course. So I think the first one is due on February 1. Oh, there's still some time, but not too much, because you have to form groups, and then you have to know your group mates, and then you have to work together, and that takes time. So you should care about it soon when we give you information about it. I think there was already an announcement that you should pick groups. Maybe I can look that up for you. So announcements here. Canvas page ready. I don't know if there's already something about groups, but you can read about it down here. So it says it's due on February 1. And yeah, you can read about it here, how it's supposed to go. So groups of 3, and the groups should be available somewhere here, maybe. I don't know. No, that's not the right one. But somewhere on this page, there are some, under people. Yeah, right, I remember, thanks. So for assignment 1, you have these groups. There are already some, and you can form groups, and in the end, who isn't in a group, we will put in groups. Okay. So that's that. And if everything is clear now, we can continue with exercise 1.5. So as I already said, we have to compare 2 types, functions from bool to t and pairs of type t. And we do the comparison by writing 2 functions like this. So let's make it a bit smaller again, called iso r and iso l. Yeah. Okay, so I have to replace these symbols again, so the compiler is happy. And oh, no, I did something weird. And yeah, that's it. So these are called ISO, like isomorphism. I don't know how much math you know exactly, but no, in this case, you shouldn't use a library function. So, I mean, if it's a small part of some large task, you can do it, but in this case, not. In this case, you should write it yourself. So, okay. We need to have a function. Could say it's a higher order function. It takes a function. Well, it doesn't return a function, but it takes a function, and then it produces something in this type, which is supposed to be a pair. So it should look like this. And to remind you, bool is something built in here, but this is what it looks like. So it's a type with 2 constructors, true and false. So now, what is the pair we need to produce here? Thank you very much. That's one way to implement it correctly. Okay, good. So what do we do now here? I guess the easiest is to pattern match and write a function here. But how can we do it? I guess there are now a couple of ways. Yeah, that's nice. We have some alternative solution for this one here. So someone else said this. Okay, let's just keep it in mind. Okay, but what can we do here? So we have a pair, now we want to give a function. Yeah, I mean, we have an idea. It's a lambda expression, which looks like this. Would be the constant function x, I guess. Yeah. That should type check at least. But I leave a question mark here. But thanks in any case. Yeah. So any other ideas? Yeah, or maybe it is the other constant function. Who knows? Yeah. Let's keep that in mind as well. We could also take this one. So which one is better? Any opinions? Or are there any other solutions? Yeah, sure. Taking the second component of a pair is, of course, the smart. Oh, yeah, let's try this one. I like this idea. So if true, return this. If true, then x, else y. Oh, we're not allowed to. But I guess what you mean is something like this, right? Yeah. You still need the lambda, right? Yeah, what about this? Are you happy with this function? So maybe since we thought about it for so long, we could explain a bit. So, I mean, if we plug in true in this function, then we map to x. Maybe let's forget about these two. And if we plug in false, we map to y. This is what should happen, right? Okay. Maybe let's experiment a bit with it. So yeah, if I just ask for this, we get something anyway. So what can we plug in? Some pair, maybe 1, 2. And I guess Haskell complains now. If no, it doesn't. Okay. Can give it a function and it returns the type. So you can think a bit about this type. It goes from bool to t. So we produced a function from a pair. That's good. That's what we wanted. And now we can plug something into this function to see what it does. So we can plug in true and we get 1. And we plug in false and we get 2. Okay, that looks good. Okay, and now maybe we should remember what we were supposed to do. What's in the exercise? Well, now it says, and show that ISO L after ISO R is the identity, and ISO R after ISO L is the identity. So both ways composing them is the identity. So now show, yeah, well, all of this stuff. So that's our next task. Well, what does it mean? One way to replace this is in math, ISO L and ISO R are bijections. So if we say we have a set of functions here and a set of tuples here, then this bijection would say these sets have the same size. We have some good way of translating an element here to an element here and the other way. Oh. And to see that these are bijections, you actually need to look at both of these compositions. Okay, don't know how familiar if you are with this kind of stuff. If that's confusing, let me know and we can talk about it some more. But otherwise, I would continue here. So what does it mean? So let's pick the first one. It is confusing. Then let's speak about it some more. Maybe I can draw a picture. Okay. So let's draw a picture. I hope you can see it well. So you can imagine sets to be like bags with things in them, like this. And at first sight, it might be, in this case, it is completely obvious that they have the same size, but if you want to figure it out, you have to give a function which gives you a one-to-one correspondence. So in this case, it could look like this. So you have one function, let's call it ISO L, which goes this way and does these kind of assignments. And I mean, now we could show directly that ISO L is a bijection by seeing it hits everything here once and only once. So it's a one-to-one correspondence. But a way you usually use in mathematical practice is, so this is one-to-one or bijection. The way you use in mathematical practice is usually that you show this and this. Yeah, and maybe one word why this works. So I mean, one way to say this would be surjective, which means everything is hit at least once by your map, and injective. And surjective, this everything is hit at least once over here. You know will be inside here because you can go back with this function. So you can apply iso r, and then if you apply iso l, you will be at the same place. That tells you it will be hit. And this injective means everything will be hit exactly once. That means if you have two things over here, and then they will be mapped to different things over here. And an equivalent way to state this is if two images are equal. So maybe let's write it like this. If you have fx equals fy, then you know x equals y. So that's logically the same as, at least classically, if these two are different, then they are mapped to different things. So that's certainly one thing a bijection should do. Okay, my format is not ideal. Yeah, and that's something, at least in this way, you can see using this. Because if you have an equation like this, let's say f is iso r, so we're using this now. So if you have, no, iso l is what you want to say, iso lx, iso r, l, y, then let me write a bit better. So iso lx, iso ly, and if you apply iso r, you can just write it on the outside here. Iso ly. But now you have just this composition here, and it's the identity. So you know x equals y, and you have shown that it is injective. That's one part of being a bijection. So that's usually, I don't know, it's usually in the beginning of a math course that you can, okay, here's a question. So like, yes, that's a good example. So example from the chat. Let me just turn to a new page. Example from the chat. On the integers, you get a bijection. So from the integers to itself by this map, and the iso r would be this map. So written in normal math style. So here you know they are inverse to each other in both ways. And that's one way to show that f is a bijection. Oh, wait a bit. So now you can hopefully see it. Yeah, that's a nice example. Okay, but back to our example. So I mean, the exercise doesn't say bijection, but that's what's behind it. And isomorphism is also a word we use for bijection and other things. So that's why it's called iso r and iso l. And yeah, let's just show those both cases, and even if you're still confused by the whole bijection thing, you might be unconfused by looking at these concrete code examples. So in Haskell, we can write composition like this. With a dot. And to show that some function is equal to the identity, well, that's a question now. What does it mean for functions to be equal? So in this point, the exercise might be a bit vague, but I mean, we interpret our Haskell code in a mathy sense. So we should think about what does it mean in math if we are in doubt when two functions are equal. So, and I would say two functions are equal if they are equal for all elements I can put in from the domain. I mean, in programming, you could also say they are equal if they have the same code or compile to the same assembly code, or you could come up with a lot of different things. But here we just say they are equal if they produce the same values for the same input. And we don't consider stuff that one function might produce a stack overflow while the other doesn't, or something like this, but they still produce the same value if they successfully run, or something like this. Yeah, we all forget about this and just say functions are equal if they produce the same values. So what I really want to show here, or what I'm asked to show, is that these two things are equal, and equivalently I can plug in this value like this, and over here that will just be x. Maybe that's a good point to use a multi-line comment. Okay. Good. Maybe we start with an example. So I started the more difficult way in terms of examples now, because my x here will be a function. But why not? I can take a constant function, which is constantly 1, and ask what it will be. So what I get back is a function again. So my little x here is a function. And if I want to test if this function is the same as the one I put in, so this maps true to 1 and false to 1, I can test it for both values. Okay, seems to be good. The notation, okay. This, in this case, it's the same as this one, I guess, yeah. So the underscore is just like a variable name, but we don't give a name to it because we won't use it. So if I want a low-tech solution more, then I should have taken this one, this case, that's the same. The lambda itself. So this is for lambda. So it's an ASCII approximation to the Greek letter lambda. And the whole thing is called a lambda expression. So something like this. Could also look like this. This is called a lambda expression. And maybe I show you on paper. So in math, people write lambda expressions like this, for example. So this is one way to denote them. Or really in high school math, you could also say the way you define functions there, like this, for example, is also close to a lambda expression. So in a way. But maybe that goes a bit far. So that's math. And the more computer sciencey way is like this. And what people also write is this. Okay. Good. Now I should just move the window. Okay. So lambda expressions, right? Yeah, okay, that went a bit far. Forget about this one. Sorry. What I should have said is, at least from my high school experience, is that you are introduced to functions in a way that is a lot like lambda expressions. Yeah, but sorry, forget about this one. Yeah. Yeah, but to answer the question, if you just use the single symbol, that's not a lambda expression. And if you do something like this, you also define a new function, which is not a lambda expression. So this, I guess, would be things for me that are more away from lambda expressions. Then you, in Haskell, you also have higher order stuff, which lets you work with functions and, well. Yeah, thanks for the explanation. Let me read it so I can comment. Yes, very good. You explained very well why this was wrong. Right, thank you. So this would be a way to define a function f by using a lambda expression. Okay, very good. Good, okay, so no, we don't talk about Y combinators now. Let's stick with the exercise. Okay, so we tested it on one thing, but what we really should do is find an argument. Maybe here it's better to call our xf, because that way we can remember that it's a function. And well, what is it really? So we can try to evaluate ISO R in a way that's Oh no, I took the wrong one. I took ISO-F. So yeah, just write it down. So like this. Okay, that's what we need to show. And if we plug in the definition of ISO-L now, what do we get? Well, ISO-L matched on a pair of x, y, and we know what our pair looks like. It's f of true, f of false. Let me just adjust this a bit. Okay. So we want to see this is f. Okay. And at this point, it might help to write it in a bit of a different way. I hope I'm writing by Haskell here. Okay, so in this way, it might be more obvious that what we get is actually true f itself. So let me explain a bit. So we have some abstract function f given here. And over here, I say we have a function that maps true to f of true and false to f of false. So according to what we said earlier, two functions are equal if they map each value of the domain to the same value. Then these two functions, left and right here, are equal. Okay. Do you agree or are you confused? Yes. So would one question is, would this hold if ISO-L is defined well as above here? And the answer is yes. So I could also have stopped at this line and said, yes, here we are mapping true to f of true and false to f of false, but I wanted it to rephrase in a still Haskell way, which is the most obvious to me. Ah, okay. You changed X and Y. Very good. Okay, good question. What happens if we change X and Y? I didn't notice, but yes. So what happens if we change X and Y? Does it still work? The answer is no. Yes, as someone else just said, it's no. because it switches our function in the end. So if we take iso r and then iso or iso r and then iso l, then we get a function that has its values switched. So yeah, maybe I'll just write it down, what I just said as a comment here. So if iso l was blah, 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 like suggested, then let me write it down. Then this of false would be f of true, and this of true would be f of false. Yes, it would. So one question is, would this function then still be a bijection? Yes, it would be. And we can see it by giving a new iso r. So, but maybe let's write it like this. Iso L is still a bijection because, or maybe let's call this one iso L prime, because we can define iso r prime of f as f of false, f of true, so a different pair. And then it would be true again that what holds? It holds that these compositions are the identity again. And that tells us iso L prime and also iso R prime are bijections. So yes, would still be a bijection, but we would have to adjust our proof by giving a different iso R. But maybe let's look at how we would finish the actual exercise. So we have some proof for that, but we also really shouldn't forget to prove the other direction. So again, in Haskell, that means for all, let's just write it like this, pairs, for all pairs like this. We should have, and let me just turn it around. Oh, no. Maybe. Right, like this, we have to prove the following. Iso R applied to iso L of this pair is this pair again. Okay. So let's just do this. Take this expression and this time try to simplify it until we get what we want. Okay, so let's try to simplify from the inside. This pair, ISO L of this pair gives us this function. Okay, that's certainly true because I just plugged in literally this definition. Okay, so let's apply this definition. Take a function, apply to true, and apply to false. So maybe I completely write it out. So I have this lambda expression. This is a function. And I apply it to true. And then my pair has another component, which I will write in a new line. And here we plug in false. And now we can just calculate. So here we have our function. We plug in true. We know that. So we can imagine to be true here. And then it's x. So we get a pair x. And the other part here, we have false plugged in for that. So we get y. So it's the pair xy, and we are done. Okay. Well, thanks for participating and all your answers and questions. And if there aren't any questions, any more questions, I would say see you sometime soon. I don't know, next week David will do the exercise demo. But yeah, until then, have a good time playing with Haskell. Bye-bye.